Today is our last week of homework assignments. I'm sure you're happy about that. And this will be the last quiz. I know it's only 6 quizzes, but that's okay. I will adjust that to make sure you do all right. I will be sending the final examination out this week as well, and it will be due Monday of next week. Normally I would have it due by Friday, but since we do not have graduation on Saturday, I can give you a little extra time to get it done. So today we're going to go over the homework assignments for nuclear chemistry. And the first few problems are fairly straightforward. The first one states, for each of the following isotopes in exercise 20.1, determine the number of protons, neutrons, and electrons in a neutral atom of the isotope. Okay, so let's take a look at first A, which is sodium, 2411. Now the bottom number here is the atomic number, and that is the number of protons and the number of electrons in a neutral atom. Neutral meaning not charged. So we have 11 protons and 11 electrons. The top number, 24, says that the atomic weight, which is the sum of the protons and neutrons, is 24. So to find the number of neutrons, you subtract the atomic number from the atomic weight. So 11 from 24 is 13 neutrons. So this first one has 11 protons, 11 electrons, and 13 neutrons. The second one, aluminum 2913, 2913, aluminum. Now the atomic number, by the way, is what determines what element it is. You look on the periodic table and whatever element has the atomic number of 13 is what it is. The number of protons in an element always determines the element that it is. So we have 13 protons. This will become important, by the way, when we start doing the equations. And neutral, so it's 13 electrons. And 13 from 29 is 16 neutrons. The third one, C, is krypton 7336. 7336. Make sure I got that right. So that means we have 36 protons and 36 electrons. And then 36 from this is 7. 6 from this is 7. And this is now 60, so 3 from 6 is 3, so 37 neutrons. D is iridium 194, 77. So we have 77 protons, 77 electrons, and then 77 from 194, 7 from 4 is 7. This goes to 8, 7 from 8 is 1, so 117 neutrons. And if you add the neutrons and the protons together, you should always get the atomic weight, and that's how you can check your answer. Number 6. Calculate the density of magnesium nucleus in grams per milliliter, assuming that it has the typical nuclear diameter of 1 times 10 to the minus 13 centimeters and is spherical in shape. Well, you know that density is equal to mass divided by volume. So we need to calculate the volume from this diameter they gave you, and we know that a sphere has a volume of 4/3 pi r cubed, and r is 1/2 the diameter. So 1 times 10 to the minus 3 is 5 times 10 to the minus 14 centimeters. Now, A milliliter, by the way, in case you forgot, is a cubic centimeters. So we don't have to change this unit in order to do this. So then we put volume is equal to 4/3 pi times R, which is 5 times 10 to the minus 14 cubed. We get a volume for this atom of 5.32 times, or 5.23 times 10 to the minus 40 cubic 40 cubic centimeters, which is the same as milliliters. Those two are the same. And so that's the volume. Okay, so now what is the mass? The mass is found by knowing that, first of all, if you look up the molecular weight, you get 24.31 AMU, atomic mass units. So what is the conversion for that? If you look in the book, you'll find the conversion is 1.6605 times 10 to the minus 24 grams per AMU. So if you multiply these two numbers together, you get the mass of the nucleus. So the mass is 4.04 times 10 to the minus 4, or 10 to the minus 23, excuse me, grams. So now we put this in our formula here. We put the 4.04 times 10 to the minus 23 grams and divide that by the volume, which is 5.23 times 10 to the minus 40. And we find that the density, which is no surprise that this is a very high density situation, is 7.72 times 10 to the positive 16 grams per centimeter cubed or per milliliter. Number 10. Which of the following nuclei lie within the band of stability shown on figure 20.2? Now, quite honestly, this is fairly straightforward. I'm not going to write anything. If you look on page 1080 of your book, you'll find the band of stability showing radioactive in green and non-radioactive in blue or purple. First one is, and it's based on the number of neutrons and the number of protons. So you have to take the various elements. You'll need a periodic table also to look at this, because they're not, on all of these, some of these, they're not giving you the atomic number, so you don't know the number of protons unless you look it up. So first, let's look at argon 40. If we look at argon, argon's a noble gas, Ar. You'll see that that's 18 for an atomic number. So it has 18 protons, and 40 has if you subtract 18 from 40, you get 22. So you have 18 protons and 22 neutrons. And you'll find that that is within the band of stability. Matter of fact, it's close to the band of non-radioactivity. So argon 40 is within the band of stability. The second one, oxygen 16. Well, oxygen 16 is the normal state of oxygen. And so without even looking, I can tell you that it will be within the band of stability because it's a non-radioactive form of oxygen. C, barium 122. Barium is in the second column, Ba. 56 is the atomic number. If you subtract 56 from 122, you get 66. So it's 56 protons and 66 neutrons. And again, you're in the green, close to the blue part of the band, inside the band of stability. So barium is within the band of stability, barium 122. Nickel 58, it's 28 for the atomic number, so that means we have 28 protons and 30 neutrons, and again, that's actually the stable form of nickel. Thallium 205, TL, if you look TL and you'll find it under, just outside the transition zone, just to the right of the transition zone. So it's 81 205. So that's 124 is the number of. So if you go to 81 and 125, it's going to be close, but it looks like to me that it is within the band of stability. Thallium 110, if you subtract 81 from 110, you get 129. And 129, 81, 129 is real close to being outside the band of stability. And then radium 226, radium is 226, radium is just below barium, is an atomic number of 88. So 226 is 126 plus 12 is 138. So 88 and 138 is also just makes it in the band of stability, but it's radioactive. And then the last one was magnesium 24. So that's actually the normal form of magnesium, so it's going to be obviously within the band of stability. The next problem is problem number 14, and this is doing some equations. Let me just change this to a 14 here. This is just doing some equations. And I'll talk you through how to do that as we move through. The first equation says that we have lithium, and it goes to form, wrote that down wrong. Let me erase this, come back. Lithium plus something goes to form 2 alpha particles, or helium nuclei. Well, they're only alpha particles if they're charged, and these are not charged, so there's just two helium molecules. Now, the general way that you do this is to remember that mass and charge have to be conserved. And so here we have a total of atomic number of 8, or atomic weight of 8, and atomic number of 4, okay? And then over here we have 7 and 3. So in order for these to be balanced, you have to have a 1 and a 1 here. Now, what has an atomic mass of 1 and atomic number of 1? Well, if you look that up, you'll find that that's a hydrogen atom. So a hydrogen atom added to lithium goes to form 2 helium atoms. That's what that shows. Let's look at B. So that's A. B says we have carbon 14 going to nitrogen 14 plus something. So you have carbon 14 going to form nitrogen 14 plus something. Now, in order for this to happen, the atomic number has to decrease by 1, okay? In order to do that, you have to have something that has a -1 but no mass. and that is an electron. Electron has an atomic number of -1 because it's a negative charge, and a relative mass of 0. This is also called a beta particle. And so if we put this here, the -1 subtracts from this to give you this. 0 has no impact on the mass, so you have a balanced equation. The third one is aluminum 27 plus helium. So we have 27, 13 aluminum plus helium, which is 4, 2, which if charged is an alpha particle, and that goes to form something, plus a neutron. And a neutron has a mass of 1 and no atomic number. It has no effect on the atomic number. So if we add these up, we have 15, and there's nothing here, so whatever it is has to be 15. And then if we add these up, we have 31 minus 1 is 30. And if you look this up in the periodic table, you're going to find that this is phosphorus. Phosphorus has an atomic number of 15, and then it has an atomic number of 15. And so that tells you that the element you're dealing with here is phosphorus, and then if the mass of that, because of the balancing of these masses, is 30. So phosphorus 1530. The last of these is a little more complicated. We have Cm 25096, Cm 25096, and it goes to form Sr 98, excuse me, 38 plus something plus 4 neutrons. I always put parentheses around these to keep things clear. So how do we go about doing this? Well, we go about doing this by, again, finding out the totals of the atomic number and atomic mass in both sides. So we have 250 for the atomic mass on this side, and 96 on this side for the atomic number. We have 38 here. There's no addition, so we have 38 for the atomic mass or number on this side total. We have 96 here. We have 4 times 1 is 4 plus 98 is 102 here. If we subtract 102 from 250, we get 148. And if we subtract 38 from 96, we get 58. So 58 plus 38 gives us 96. If you look in the periodic table, 58 is Ce, or cesium. And so the balancer is cesium 148 is the answer to this one.